us also go back. We have written this CLT will be what? CL alpha tail into alpha tail plus CL delta E into delta E. We are assuming that CL naught is 0, assuming things will be symmetric, aerofoil is symmetric. Now, we are assuming CL naught, let me write this, equal to 0. Now see, at trim, when hands off, or I don't write at trim even, let's say in a hands off condition, what will be the CL? CL tail will be CL alpha T into alpha T plus CL delta E into delta E float. Right? That is the final CL you required, and that is why I was writing at trim, that is the CL trim. At that trim, your CL will be CL alpha tail into alpha tail plus CL delta E into whatever delta E has floated. Now, how much delta E will float? That I know. CL tail equal to CL alpha T into alpha T plus CL delta E. And for delta E float, I write CH alpha T by CH delta E into alpha T. Let me repeat again. At alpha T, delta E also will float. So whatever lift or lift coefficient the tail is seeing will be CL alpha T into alpha T plus CL delta E into delta E float. Okay? And that I am writing here as CLT equal to CL alpha T into alpha T plus CL delta E. Instead of delta E float, we are putting this term expression. Right? So finally, what is happening? Finally, it's interesting to see what is happening. Then I can write CL tail equal to, let me write this, CL alpha T 1 minus CL delta E by CL alpha T into CH alpha T by CH delta E into alpha T. This is clear? From here, I have taken alpha T common, CL alpha T here, and I have taken CL alpha T also common, so that one CL alpha T will come downward, and rearrange this term. I could write it like this. And what is CL delta E by CL alpha T, and what is CH alpha T by CH delta E? We should not forget that these are related to hinge moment properties, and these are with the elevator tail combination, that property. Okay? So now you know that CL delta E by CL alpha T is nothing but d alpha T by d delta E, and which is in notation wise we say tau. What is the physical meaning of this ratio? It comes mathematically as d alpha T by d delta E. That means per unit change in elevator deflection, how much tail angle of attack effectively is changing. It's a very, very important performance parameter in design in terms of tail performance parameter, and that is denoted as tau. And you will see that when you solve an example, this tau can be estimated through some empirical relation which goes as, I'll give you the right figure for this. It varies with AC by ST, that is elevator area to tail area, and typical value for most of the airplane into lie between 0.4 to 0.6. That's a good enough a value. Okay? This exact numbers we'll be using it to do our numericals. Now let us come back to this. If this is the understanding where we are approaching to. So I can write CL tail as CL alpha T into 1 minus tau CH alpha T by CH delta E into alpha T, and I denote this as F. So I can write CLT equal to F into CL alpha tail into alpha T, or further I can write with the float, it is CL alpha t prime into alpha t. Note down this. If it was not floating, then it is CL alpha t into alpha t. Now because of floating I have put prime, so that make distinction. Okay? And what is F? We could see F will be less than 1 because this is negative, this is negative, this is positive, so F will be always less than 1. So what we are getting is from this relationship CL alpha t is greater than CL alpha t prime because this part is nothing but CL prime alpha t is nothing but CL prime alpha t, nothing but F into CL alpha t. And F is less than 1, so I can always see that the CL alpha t is greater than CL alpha t prime when it has been permitted to float, the elevator to float. What is the physical meaning of this? Let us understand this. Okay? It's very simple, and you will appreciate once you understand the mathematical part of it. Let us see what does it mean. Let us say this is your elevator, okay, and this is my equilibrium, right? I'm writing everything that is stick fixed. I am not allowing any alpha t. I am not allowing this to float. But actually, if you put hands off, it will actually float and come to an equilibrium. So the new equilibrium will be something like this, which is with delta E float. So now actually if I try to find out what will happen if I try to move the airplane from this configuration to another configuration, so I take this as an equilibrium, and this equilibrium you could see that since it has floated up, its CL alpha has to reduce compared to the first case. You know, if you do a camber, it will further increase. So that is why, since it has floated up like this, its CL alpha has to be less compared to CL alpha when the stick was fixed. It was not allowed to float. So what is the message? Whatever you have developed, expression you have developed for a stick fixed case, you can use those expression, but for change the CL alpha tail by CL alpha prime tail. That's all. Is it clear? I repeat again. Whatever expression you have developed, that remains same, except wherever CL alpha tail is coming, you change it by CL alpha t prime. You will get expression for a stick free case. Okay? So let us do that. Let's see, for a stick fixed case, CM CG was CM naught plus DCM by DCL into CL, stick fixed. For stick free, what will happen? For stick free, it will be CM CG will be equal to CM naught prime plus DCM by DCL prime into CL. I will, for time being, I will not bother you with CM naught. Focus on DCM by DCL prime. What is the meaning here? It is stick fixed and it is stick free. Okay? How they are different? If CM versus CL, let's say, this was for stick fixed. Now for stick free, what has happened? For stick free, the CL alpha tail has reduced, right? For stick free, now the aerofoil is, the elevator has moved up like this in equilibrium, right? It has floated at a given alpha t, delta E float. So its configuration is like this. So this will reduce CL alpha T, and as CL alpha T reduces, the static margin also will reduce, right? So it will be for stick-free case, if I am modeling through stick-free case, it will be something like this. And that is why I did not join them at CM naught, because CM naught prime I have removed. It will unnecessarily create confusion. It doesn't make much of a difference, but yes, there will be slight difference. But at this point, please understand, we are not telling that pilot will be flying stick-free or stick-fixed. This is for our modeling. To stick-free, we are doing to ensure that I can model stick force with the speed or CL. As far as pilot is concerned, there is a fixed delta E required, which is given by delta E naught plus d delta E by dCl into CL trim. Okay? That is the delta required. I repeat, in one case, you take it to that 5 degree or 4 degree and fix it, lock it, stick fixed. Another, now we are doing one more thing because we want to develop a stick force relationship with such deflections or speeds. So we are telling, let us also see that since the elevator will float, how much effort pilot has to put through his force to see that it again goes back to 5 degree. Okay? But if it is 5 degree, it is 5 degree. Correct? I again repeat, somebody asked me question, is the pilot flying at stick free or stick fixed or stick fixed? Absolutely irrelevant question. Pilot needs to give a fixed elevator deflection to trim the aircraft a particular CL trim. As simple as that. Okay? So this is one thing you understand, that DCM by DCL stick fixed will be more than DCM by DCL stick free. In a sense, it will be statically more stable compared to that as far as the mathematical term is concerned, because we have changed the equilibrium now. We have allowed it to float. Okay? CM naught is given as CM naught wing plus CM naught fuselage plus CL alpha tail VH neta T into IW, all these things you know by now, plus epsilon naught. So CM naught for stick-free case will be, as you see now, will be CM naught wing, which has nothing to do with elevator floating. CM naught fuselage, nothing to do with this, plus CL alpha tail. Now it will become prime, and rest remains same. You remember IW is the wing setting angle, IT is the tail setting angle, and epsilon naught is the downwash at alpha equal to 0. Typically, it is for cambered wing. Now, what about DCM by DCL? DCM by DCL, for a stick fixed case, it was XCG bar minus XAC wing. We have all developed this, plus DCM by DCL fuselage, FS I mean fuselage, minus CL alpha tail by CL alpha wing into VH into neta T into 1 minus d epsilon by d alpha. This was for stick fixed case. So from this expression, you can easily write DCM by DCL free will be nothing but XCG, that is not going to change because something has floated, XAC wing minus DCM by DCL fuselage, and then minus, now CL alpha T prime will come here. CL alpha wing, VH, neta T, 1 minus d epsilon by d alpha. So nothing new we are doing. We have agreed that because we are allowing the floating tendency, the stick is not fixed. So the elevator will go to a particular delta E and it will set, delta E float and set. So the curvature will change. It will be going up like this, so CL alpha tail will change once you allow elevator to float. So this is this, and then, okay, this is fixed free. We want to know the neutral point. And for neutral point, let me erase this, write this expression, and you go home happily that you have now know how to handle the stick-free case. Most of the books are not giving you explicit thing because this concept is out of market. As you understand, most of the controls are irreversible now, right? So for neutral point, again I take the stick fixed case. It is X AC wing minus DCM by DCL fuselage plus CL alpha tail by CL alpha wing VH neta T to 1 minus D epsilon by D alpha. So what will happen for stick free neutral point XNO prime, which is stick free neutral point? This will be again XAC wing minus DCM by DCL fuselage plus now CL prime alpha T by CL alpha wing VH neta T 1 minus D epsilon by D alpha. Is it clear? So what I told you, as long as you understand, because you have allowed the floating of the elevator, the CL alpha tail is changing. So if I know the expression for a stick fixed case, I can find out the expression for stick free case. Correct? Just to conclude this part, you may ask me a question that how did you find stick free neutral point and how did you define stick free neutral point? So for that again I am going back to stick fixed case. In a stick fixed case, how did you define XNO or neutral point stick fixed? What was the definition? You know DCM by DCL is given by this expression. Now we ask a question, what is that CG location? What is that CG location at which DCM by DCL is 0? That the aircraft becomes neutrally stable. And that is called stick fixed neutral point. And there what you do, you put this equal to 0 and then find out this XCG. So all this term will go to the left hand side. That is how you got the expression for X naught stick fixed. Now similarly for stick free case, for stick free case, what will be your expression DCM by DCL? What will be the expression for stick free? You are now expert. It will be all same except here CL alpha T prime. And you know the CL alpha T prime is nothing but CL alpha tail into F. And F also you know what is, how to expand it, right? So now if this is DCM by DCL free given by this expression, for stick free case, what is the condition? What is that CG location at which DCM by DCL free is equal to 0. Simple as that. So now you put 0 here, and then this is your, then it becomes X naught prime, and you get this expression as we have written earlier. Clear? But a word of caution. I repeat again, if we want to trim an airplane for a particular CL, this is governed by simply by this, that if I have to trim it here, then I need some delta E required. And that angle, if it is 5 degree, it has to be 5 degree only. It has nothing to do with stick fixed or stick free. Stick fixed means I take that angle to 5 degree and lock it. Because I know if I leave it like that, then the elevator will float. Second thing is, in a stick free case, what we are trying to do, we are trying to model, develop background to model stick force, how much stick force is required. In the stick fixed case, what we are answering is how much delta E required. So this is a subtle difference in the modeling. In the stick fixed case, our focus is on how much delta E is required. And that is the final, that much delta E is necessary to be required to fly at a particular CL governed by that delta E equal to delta E naught plus d delta E by dCl into CL trim. In a stick free case, why we are modeling this, we understand if it is a reversible control, then can I relate stick force to the elevator required, and can I fly hands off? That is, I put the hands off, and after a certain point, the elevator float itself will take care, and pilot has to put that much of force to give that additional thing, that totally automatically after floating it will go to 5 degrees, and I can fly hands off. That's the concept, to give a concept to develop a mathematical model to relate stick force with the flying condition CL or speed, right? So please keep this back of your mind, and this concept of stick-free neutral point is only true for reversible control, but unfortunately most of the airplane now have gone into irreversible control. Just for completion, I'll be taking perhaps one more lecture on this. So let us again revisit when we are talking about floating tendency or a stick-free case. What is the necessity to define a stick-free case? Please recall, we know one thing, that if an airplane is flying at this CL, so this is the CL, now you want to fly at this another CL, then you know that so much of negative pitching moment the aircraft will generate by itself. So if I want to really fly at this point, I must ensure that this negative moment is neutralized by giving the elevator up from the reference elevator angle, and I need to know how much this delta E, which I call delta trim or delta E required. If I know that, then I can trim the airplane, which was earlier trimmed at this CL. From this CL to this CL, I can do that by putting this much of delta E trim. Who decides how to calculate that delta E trim? Please understand this. This delta E trim or delta E required, whatever you say, will be given by delta E naught plus d delta E by dCl trim into CL trim. And if I carefully see d delta E by dCl trim, this is nothing but minus dCm by dCl by Cm delta E, approximately. We have seen that. dCl trim, when I want to use minus dCm by dCl, this is actually minus dCm by dCl, stick fixed. Divided by Cm delta E. Stick fixed means control locked. We are not allowing it to float. That is important. So what is delta E required is decided by dCm by dCl fixed. And that dCm by dCl fixed or dCm by dCl stick fixed is nothing but, you know that dCm by dCl fixed is minus static margin, so minus x n naught by xcg. I put bar. By now you know bar means non-dimensionalized with mean aerodynamic chord. So the important is here the n naught will be again stick fixed. Okay, this is very, very important, that when I am going to trim, how much delta is required is decided by this dCm by dCl stick fixed. As simple as that. That you should understand, and you should not start thinking of whether to dCm by dCl free or not. Delta E required is governed by this dCm by dCl fixed, by this, through this expression. We need to also understand that what is the physical meaning of d delta E by dCl trim? Many times I write it as d delta E by dCl, but you understand that is d delta E by dCl trim. Meaning thereby, suppose at this point it has a delta E equal to delta E1 to trim this here, and at this it is delta E equal to delta E2. So d delta E by dCl trim is that gradient that is from delta 2 minus delta 1 by Cl2 minus Cl1. Cl2 is a trim, Cl1 is again a trim, right, at different condition. So that is the meaning of d delta E by dCl trim. Okay, this is very important because many times students they get confused. Please understand, when we talk about floating tendency, we were being telling that we are developing this concept to give a feel for the pilot through stick force, which we will see how we build it up. Because if we are talking about stick fixed like this, which is very important to decide how much delta E is required and how the pilot will develop the field, he will say, okay, for a given Cl, this is the delta E required, this is Cl1, delta E2 for Cl2. So he will be seeing that how much delta E required for a particular Cl or particular speed. From there he develops a field. For example, for same Cl, so Cl remaining same, if one aircraft required delta E equal to minus 4 degree, another aircraft for same Cl, for same condition, it requires delta equal to minus 6 degrees. And the pilot understands that the aircraft number 2 is statically more stable because it requires larger control effort. Okay, so that way you can give a field which doesn't have a direct one-to-one contact because it's visual. This much delta E, this much Cl, this much delta E, this much Cl or speed. But if you want to really give a feel to the pilot, okay, then you have to, one way is to do is that, okay, what is the effort pilot takes to change the elevator from one angle to the another angle? What is the amount of stick force he is applying? So that is also another way of giving a feel to the pilot. To develop an expression so that we can quantify, we can develop mathematical model to develop a feel for the pilot, there we are using the concept of stick-free stability. Okay, I repeat again, only to develop a mathematical model to give a feel for the pilot, we are talking about stick-free stability, or we are building the concept of floating of the elevator. So this is very, very important and you should not get mixed up. If you ask a question to yourself, finally, if I want to fly at a particular CL, how much delta E I require, you have to only use this where you are very clear this is nothing but dCm by dCl stick fixed or controls locked or elevator is not allowed to float. Clear? Right? This should be very, very clear in your mind. Thank you very much.